Hi students, today I'm going to explain about the ring and twister ring counters which are in the module 5th. In the previous lectures, we discussed about counters, what is counter and how many types of counters. This is the basic important application in the sequential circuits. So among those counters, we need to discuss this ring and twister ring counters. Basically, we know that the counters are constructed with a series of flip-flops. Based on the input and the clock pulses given to the flip-flops, there are different types of counters. Asynchronous counters, unsynchronous counters, decade counter, ring counter, and Johnson counters. So, and one more thing is, there is a ring and Johnson counters are like we directly given to the one flip-flop is connected to the other flip-flop and clock is given. In the ring counter, it is a special type of application of the serial in and serial out shift register. We have known that shift register, a group of flip-flops connected together to shift. The input is given to the one flip-flop. It is shifted by one flip-flop to other flip-flop and passed by to the last flip-flop. Serially, by the application of the clock, the output is collected at the last flip-flop. So as the application of the clock, each flip-flop sent to the neighboring of flip-flop by one bit. So whatever the data which is given to the first flip-flop is come back come out of the last flip-flop based on the number of flip-flops. For example, 4 flip-flops are there. So we have given this first bit at the input of the left side of the first flip-flop. After 4 clock cycles, the first bit comes out at the last flip-flop. Likewise, in the next clock sequentially, the next clock, the next bit is coming serially. So in that particular application of this shift register, we can see that this ring and Johnson counters are among those shift registers. We can make these shift registers with more useful. So that's why this ring counter is a special type of application of the shift register, SISO shift register. The only difference between the shift register and the ring counter is that when we see that the last flip-flop output is taken as the output in the shift register. The input is given at the shift register at the first flip-flop. The output is taken at the last flip-flop. In contrast, in the ring counter, this output is passed to the first flip-flop as an input. In other words, we can say that the output of the last flip-flop is taken back as a feedback and given to the input of the first flip-flop. So this is the difference between a ring counter and a shift register. As we can see that number of stages in the ring counter is equal to number of flip-flops used. Sometimes it equal number of flip-flops less than or equal to number of stages. This is general case of the counters. So in the ring and Johnson counter, it might not apply. The block diagram of the 4-bit ring counter, if you see that. This is the block diagram for the ring counter. As it says, it is a 4-bit ring counter. It requires 4 flip-flops. You might take this and we can design this ring counter with the help of D flip-flop. So take the 4D flip-flops. Here it is connected. We can represent these 4D flip-flop with the names FF0, FF1, FF2, FF3. It has a input. These are having inputs D0, D1, D2, D3. Take these 4 flip-flops one by one, like side by side, and the first flip-flop output is connected to the input of the second flip-flop. Second flip-flop output is connected to the input of the third flip-flop. Here we can say that D2, and third flip-flop output Q2 is connected to the fourth flip-flop input D3. And the last flip-flop is feedback taken back and connected to the input of the first flip-flop. So Q3 is connected back to the input of the first flip-flop. Name it can be called as D0. And if it is a sequential circuit, it must require the clock, and also it is a counter based on the clock pulse application. So that's every time it needs to be changes of its states. So we can connect clock. So clock is one of the input. This clock is connected to each flip-flop synchronously. It is our wish to provide this positive edge clock or negative edge clock. If it is negative positive edge clock, we can represent with as normal representation. We need, for example, if we require negative edge clock, whenever the events need to be changed by 1 to 0, we need to provide some bubble. This is represented by negative edge clock. Whenever clock is changed from logic 1 to logic 0 transition, then the states in the flip-flops or states in the counters has to be changed. So this type of negative edge trigger used in this ring counter, and we are ORI input is connected to two asynchronous inputs which are called preset and clear. So here it is, in this connection of ring counter, we have just connecting preset for the first flip-flop, and the remaining all are connected to clear inputs. So these are clear inputs, asynchronous inputs. 3 clear inputs are connected with this flip-flop 1 and flip-flop 2 and flip-flop 3, and only one asynchronous input called preset is connected to this first flip-flop FF0. This is the block diagram. We can say that take the 4 flip-flops connected side by side, and first flip-flop output is connected back to the next coming flip-flop, and the last flip-flop is fed back to the first flip-flop. So clock is connected to all flip-flops synchronously, and ORI connected back respectively. The same clock pulse is passed to the clock input of all flip-flops as a synchronous counter. As I said, the ORI, which is called override input, is used to design this circuit where it is used as a clear and preset. Most of the time these asynchronous inputs are helpful, they are used for initializing of the counters with the zeros and with the ones. If we need to clear all the flip-flops at a time, we have just initiated that clear input, whether either it is active low and active high. Most of the time they are active low inputs. With the help of these asynchronous inputs, clear and preset, we can, if you want to clear, active low is like given to the clear input. It clear all the flip-flop output stages. When all the flip-flop states are in an initial state like zeros, then the actual counting process started. Sometimes it requires to preset of all inputs, like preset of all states is equal to 1. Then we can enabling the preset input by providing the logic active low input to the preset. Then they will become, the outputs will become as a logic 1. Then the counting started. For example, if you step down counter initialized with all logic 1s in the all the outputs of the flip flops, then it requires to preset of all outputs. So based on your requirement, you can make them, you can use them, those asynchronous inputs of clear and preset. So these can be these overriding inputs used in this ring counter based on our requirement. So it is connected. One overriding input is like preset is connected to first flip flop FF0, and the remaining overriding inputs clear given to flip flop 1, flip flop 2, flip flop 3. Because in our case, when we are in the ring counter, so in order to start the counting, so when we need to connected this feedback connection with initial value of all flip flops with zeros. If you are not providing this ORI preset input to the first flip flop 1, so if you assume that if it was not there, then all initial values of zeros in the all outputs are like rotating continuously. So no state changes at all. So it is keep on zeros, all outputs are zeros. That output is feedback to the input. Again, by the application of the clock, that 0 is passed to the next flip flop, 0 is passed to the next flip flop. Again, 0 is feedback to the input. So there was no counting at all. There was no changing states of at all. So in order to change those actions, we need to provide the preset at the first flip flop. So once we provide the preset at the first flip flop, then application of the clock, that preset value providing the logic 1 for the first flip flop, that logic 1 is move on to the next flip flop. If you see this, as I said, preset is equal to 0, that particular output, that particular flip flop Q is equal to 1. If clear is equal to 0, that particular Q is equal to, that particular flip flop output is equal to 0. So these two values always fixed and are independent with the input D and the clock pulse. That's why I would say they are asynchronous inputs. They are not dependent. They are not depends on the clock, and they are not depends on the input. They are independent, and also it is just like a non-maskable interrupts. So they are interrupting the flip flops at any time. Once they are initialized, once they are enabled, then irrespective of the clock, irrespective of the inputs of the clock of the flip flop, so they do their job. Yes. So the clear and preset inputs are active low inputs. Active low inputs means, here it is, whenever they are we are providing active low inputs like 0, they get enabled. So they enabled by the input of logic 0. They disabled by the input of logic 1. That's why they are called active low. Active when low input is given. Active high, whenever the other case, active high inputs means active when high input is given. So here in this case, in the ring counter, what we provide this clear and preset are called like arts said to be active low input. The output 1 is, the output is 1 when the preset is set to 0. The output is 0 when the clear is set to 0. So here we can set to 0. We can set to 0 to preset of preset. It's also called logic 1 of all flip-flops. When we set to 0, that means clearing of all flip-flop to 0. So each time we are providing active low inputs logic 0 to the preset or clear. If you want to preset of all flip-flop, we need to provide 0. If you want to clear all flip-flops with a 0, then we need to provide 0. The ORI input is passed to the preset input of the first flip-flop. In this ring counter especially, the flip-flop FF0 is the first flip-flop. So this ORI input is passed to the preset input of the first flip-flop, that is FF0, and it is also passed to the clear input of the remaining 3 flip-flops FF1, 2, 3. As I said, the preset input set to 0 for the first flip-flop, so the output of the first flip-flop is 1 and the output of the remaining flip-flops are zeros. So now when we say this thing to the ring counter, by providing these asynchronous inputs of the set to 0 to the preset and set to 0 clear at a clock pulse at t is equal to 0, then our first flip-flop is logic 1. The remaining flip-flops are zeros because we are providing preset connection to the first flip-flop and a clear connection to the remaining 3 flip-flops. Once we are providing the logic 0 to the preset and clear, and then like preset is 0 and clear is 0, then 1 0 0 0 is the initial value of the counter. When the ORI input is set to high, the low clock pulse signal is passed as the negative clock edge trigger. Once this ORI input set to high, providing the active high input, so that disabling of these 2 preset and clear signals, which means immediately the same time, so we are providing the clock pulse, the low clock pulse signal, that is nothing but negative clock edge signal is activated of the clock pulse to the ring counter. So we can provide such that the negative edge clock pulse is applied to the ring counter. A ring forms the preset 1 is shifted to the next flip-flop at each clock pulse. So every time when we are providing the clock pulse, that whatever we are assigning the preset 1 in the first clock pulse, first flip-flop, that logic 1 is shifted to next flip-flop for the 1 clock pulse and shifted to the next flip-flop for the next clock pulse. Likewise, it will be repeated until it will be reached to the last flip-flop and get back to the input to the normal initial position. Let us see the same thing in a figure. So 4-bit counter, 4 states are possible, which are as follows. This is the truth table. By seeing this truth table, we can see now there are 4 flip-flops, 4 outputs, Q0, Q1, Q2, Q3. These are the outputs. And we have 2 inputs. One is clock as usual, and then ORI inputs. What if ORI is logic low? In other words, active low. In other words, which enables the asynchronous inputs preset and clear. So whenever given to the ORI input low, then preset is active. When preset is active, the preset is connected to the first flip-flop FF0. That will make the logic 1 in the first flip-flop output. And what if the clear input, which are connected to the remaining 3 flip-flops, flip-flop 1, 2, 3, which will make them clearing of all outputs, Q1, Q2, Q3, which results 0, 0, 0. So 1, 0, 0, 0 is the initial value of the ring counter. What if ORI is turns are changed to logic low to logic high. When logic low to logic high in the next clock, so all the synchronous asynchronous inputs are preset and clears are disabled. So here it is not at all work on the preset and clear. Only it will now onwards, based on the clock application, the flip-flops, the states of the flip-flops need to be changed, and that will be passed to the through flip-flops. So when ORI is equal to high, the clock pulse changed from logic 1 to logic 0, we can represent it as low or active, like a negative edge trigger. So when we see that negative edge trigger of the clock, then what happened? The first flip-flop 1 is readily available at the D0. By the application of the clock, negative edge clock, that 1 is shifted to the next flip-flop. That 1 is shifted to the input of the next flip-flop. What is the input of the next flip-flop? Q1. The output of first flip-flop Q0 is 1 available initially. That 1 is connected to the input of the next flip-flop D1. So that D1, once clock is applied in the second time, that 1 is passed to the second flip-flop. Now, what is this 0? Because of in the ring counter, the last flip-flop output is feedback to the input. So the last flip-flop output is basically this one in output is 0. That is feedback to the input of this 0. And this one is passed to this one. Second. Now, I am applying the clock again. When I am applying the clock, again in the next time when the negative edge clock occurred, whatever the second stage, in the second stage the output of the last flip-flop is feedback to the first, and this one, the first flip-flop output is connected to the passed to the second flip-flop output, and the second flip-flop output previously, that one is passed to the next flip-flop. So then one is moved to the third flip-flop output now. Again I am applying clock here. What is the output now here? Here it is 0. This output is connected back to the input. Previously, first output is 0. First flip-flop output is 0. That will be passed to this. Sorry, this one. If not flip-flop is 0, output is 0. That will pass to the flip-flop 1. Flip-flop 1 output in previous is now it is passed to the flip-flop 2. And flip-flop 2 output, which is nothing but 1, is passed to the last flip-flop. Again I am applying the clock. This last flip-flop 1 now, that will pass to the feedback to the first flip-flop. So logic 1 here. Previously this first flip-flop output is 0, that will pass to the 0. Previously the second flip-flop output is 0, that will pass to 0. And previously the third flip-flop output 0, that will be passed to the 0. So again we'll back 1 0 0 0. Totally, in order to get this again the same initial stage, in between how many stages are there? 1 2 3 4. 1 2 3 4. 4 stages are there. So in the ring counter, with an example of 4-bit, flip-flop, 4 flip-flop ring counter, it will count 4 states. It will count 4 times. Again, after 4 times counting, again it will become in the initial state. Again, when we apply the clock pulses, again the same 4 states has to be repeated, and again it will become 1000 initial state. Likewise, in the ring counter, we will get this straight ring counter, 4 states. And one more name of this straight ring counter is referred as one hot counter. Does means one hot means at a time only one logic one is there in the sequence. If you see any sequence, only one logic one, 0 0 1 0 0 0 0 1. In all stages, only one logic one is there. That means one hot counter. This is the timing diagram for the one hot counter or a ring counter. So in timing diagram, we just check out with that. What if ORI logic low? When ORI logic low, all flip-flop Q0, Q1, Q2, Q3. In our case, when ORI is equal to 0, in our case, Q0 is equal to 0, Q0 is equal to 1, remaining all are zeros in our particular diagram. So once it is initialized by the 1 0 0 0, again the negative edge clock of the clock pulses. In the diagram, that will become, for example, here it is positive edge clock. In the positive edge, we assume that it will be active with the positive edge clock. This positive edge clock, that 1 0 0 shifted to like this one is 0, this one is passed to next clock Q1, remaining are at zeros. So 0 1 0 0. It will hold on. Again it will be this clock pulse 1 to 0 to 1 clock pulse. Again this will become 0 0 1 0. In the next clock pulse it will become 0 0 0 1. In the next clock pulse, once 4 clock pulse completed, in the 5th clock pulse it will become initial values 1 0 0 0. So likewise, in the timing diagram, we will get each 4 clock cycle, it will get the, again it will become initial values. Coming to the next counter, which is called Johnson counter, which is also similar to the ring counter. Let us see that what is the small difference between this Johnson counter and a ring counter. The only difference between the Johnson counter and ring counter is that the output of the last flip-flop is passed to the first flip-flop as an input, whereas in a Johnson counter, the inverted output Q bar of the last flip-flop is passed as an input. The only difference is that the feedback connection from the Q is called ring counter. The feedback connection from the Q bar is called Johnson counter or twisted ring counter. It is also known as twisted or switch tail ring counter. In Johnson counter, the number of stages in the Johnson counter is equal to number of flip-flops used. Number of used states are 2 into n. Let us see that why it is called 2 into n. And once it is 2n are the used states, so we know that n flip-flop nothing but possibles of states are actual possibles of states are 2 power n. But in the Johnson counter we used only 2n states. So what about the remaining states among 2 power n? So it is number of unused states is equal to n minus 2 power n or 2 power n minus 2n. Logic diagram for the Johnson ring counter. As we observe that, take the 4 flip-flops connected in series, apply the clock pulse for all the flip-flops. If it is positive edge, otherwise If it is negative edge, we can take the bubble. And providing the clear. Here is this is also one of the difference in the ring and Johnson counter. We can take this asynchronous input of clear. Only clear inputs are connected to all flip flops. Why I am connecting only? Why I am taking the clear? Only clear input means. So now, with the help of the last flip flop Q bar feedback connection, I can make this initial value of 1000. In the previous class, if we are not getting 1000 by just simply connecting Q4 feedback to the DN. But here Q4 bar, initially all flip flops are zeros. What does it mean? Q4 bar means 1, logic 1. All flip flops are zeros. So we know that flip flop outputs are always complement each other. When Q4 is equal to 0, Q4 bar is always 0. Once apply the clock pulse, this one is feedback, one is passing through the D1. So no need to provide the preset input to the first flip flop. Directly we can connect all the clear inputs to the all 4 flip flops to make the clearing of all flip flops. In the ring counter, just like ring counter, D flip flops are used in the 4-bit Johnson counter. The same clock pulse is applied to all the inputs of the flip flop. Now see that operation. Here it is. Initially, by providing the logic active low, input is connected to the clear. Irrespective of the clock pulse, we are clearing of all outputs of the flip flops 0, 0, 0. Now, what if that a clear input is logic high, active high? When it is active high, so no work on the asynchronous inputs of clear. So now the operation is based on the clock pulses. Each active low input of the clock, when applying the clock pulses, we know that all our initially outputs are zeros, and also at the same time the Q4 bar 1 is available at the input of D1 now. Initially, not output. Initially D1 is 1 is available. Once clock pulse is applied in the immediate clock, whatever the 1 is available at the D1 is passed to the Q1. So Q1 is equal to 1, remaining all are zeros passed to the 3 flip flops. Again, for the application of the negative edge clock or the clock pulses, whatever the logic 1 output available existed in the Q1 passed to the Q2, and Q2 is passed to 0 to Q3. This one is passed to 0 here. And then this complement, Q4 complement is feedback to the input, available and passed to the input. This complement of Q bar is available at the input Q1 and D1. That D1 passed to Q1. That is called 1. Now again I am applying the clock pulse in third time. When clock pulse is applied, now see what is this one? Complement of this complement of Q bar. Q bar is 0. Complement of Q bar is equal to 1. 1 is available in the D1. That will pass to the Q1. So 1. This one is passed to 1. This one is passed to at the same time 1 to here. This 0 passed to here. In the next clock pulse, now Q4 is 0. Q4 bar is equal to 1. That is readily available in the D1. So in the next clock pulse, the D1 passed to Q1, you will get 1. Already in this Q1, 1 is in previous, that one is passed to Q2. This one is passed to Q3. This one passed to 1. So 4 ones are now. Now Q4 is equal to logic 1, nothing but Q4 bar is equal to 0. That 0 is readily available on the D1. In the next clock pulse, that 0 will in the Q1 output. That 0 appear in the Q1 output. So then this one is passed to 1. This one is passed to 1. This output is passed to 1. you will get 0 triple 1. Now Q4 is equal to 1 means Q4 bar is equal to 0. That 0 is back to first output. This 0 is coming to next output. This one is coming to next one. This one is coming to Q4. So again Q4 is 0 means Q4 bar is 0, 0, this 0 step into Q2, this 0 step into Q3, this one is into Q4. Now Q4 is equal to 0, Q4 bar is equal to like Q4 is equal to 1, Q4 bar is equal to 0, that will 0 become Q1 output, this one become 1, 0, this one becomes 0, this 0, 0. So again at last we will again become with the initial values. After how many states? So if we count it for 4-bit Johnson counter, we will count it as 8. Initially 0, 1, 2, 3, 4, 5, 6, 7, 0 to 7 we will get. Again in the 8th state we will get initial values. Totally if you count here, count from this place 1, 2, 3, 4, 5, 6, 7, 8. So it is a n bit counter. You will get 2 n states. If you see this timing diagram, simply we can take that I'm taking this just 1 clock. So here it is clear. All Q1, Q2, Q3, Q4, all zeros. For the next clock pulse, this Q4 bar, Q4 is become high, remaining all are zeros. The next clock pulse, this will 1, 1, 0, 0. Likewise, it will be going on. For first 4 clock cycle, it will become 1, 1. Again, it will be changed to 0, 0, 0 after 8 clock pulses. This is about Johnson counter, and we see that Johnson counter counts twice the number of states the ring counter can count. 4-bit ring counter can count only 4, but whereas in Johnson counter it's 8 states. The Johnson counter can also be designed by using D flip-flop or JK flip-flop. The data is counted in a continuous loop in the Johnson counter. So the data count in a continuous loop in the Johnson counter. The circuit of the Johnson counter is self-decoding. What about disadvantages? The Johnson counter is not able to count the states in a binary form like 0001, 0010, 0010, 11, 0100, like that. We can't count. So if you see that output or like a truth table of the counter, so we can't see that the sequence of binary. In the Johnson counter, the utilized states are greater than the states being utilized. So basically 4-bit means 2 power n possibilities of states, but we can only 2 into n. So this unused state 2 power n minus 2n. So those states are more what states utilized. So these are the disadvantages. So this is about a ring and a Johnson counters. So it is simple. So by studying these 2 counters, we will use in a shift register application of the shift register. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.